Hey everybody, this is Mr. Ainsworth, and we're going to get into Chapter 10 here in Modern Math, or what's called Discrete Mathematics here. And we're going to talk about the dynamics of population growth. And through this chapter, Chapter 10, that is, we're going to go through three models of population growth. So let's just jot those down off to the side. Three models, okay? Three models, okay? In 10-2, okay? 10-2, we're going to talk about the linear growth model. Just giving you an overview of the chapter here. And in 10-3, we're going to go over the exponential model. Exponential model. And if I choose to do 10-4, we'll go over the logistic model. Well, that may depend. I don't know. We'll see. All right, so this first intro portion here in 10.1 gives you an idea of the terminology used when we discuss population growth. And there's a lot of terminology and because there's a lot of application here. So let's get right through it here. Today's just the intro, like I said, talking about where you see these topics here in real life. So when we talk about population growth, we're talking about creating mathematical models to demonstrate, all right, both positive uh, and negative, which is a decreased growth population. So positive growth would be indicating an increase in population, negative growth, a decrease or decay in population, no matter what it may be. It may be talking about people, maybe talking about bacteria, let's say in biology or something like that. Okay, so if we're talking about population, it could be a positive or a negative growth happening here. The types, oh boy, the types of population studied, they vary big time, okay? We may be studying human population growth, all right? Humans, all right? We could be studying animal species. Okay, we also could be talking about plants, all right? And also, we could be talking about inanimate objects too, like money. Okay, inanimate, and gotta spell it correctly here. Let's try that again. Inanimate. Okay. Objects. All right. Two, such as money. Okay. We're going to study how money grows, guys. Okay. Because it does when you invest it, that is. Okay. It doesn't grow if you spend it, but if you invest it in either mutual funds or in a bank account, which earns interest at different methods, it does grow. Okay. We'll study that too throughout the chapter. Now, modern disciplines here use study population growth as well, and one such discipline is called mathematical ecology. Okay, ooh, mathematical. All right, ecology. Another one is population biology. All right, and here's a good one right here: the study of diseases. Okay, epidemiology. Okay, epa, and then demiology. Ever see epidemiology? Okay, study of cancers and diseases and such in terms of health studies. Okay, epidemiology are built around what are called the mathematics of population growth. Okay, now in the study of population growth, there are two types. All right, could be studying what's called continuous growth, or we could be talking about or studying discrete growth. So it'd probably be good to talk about a little bit of each. All right, now the dynamics of change are in effect at all times. Okay, for continuous growth, we're talking about growth at all times. Okay, so let's put this in quotes. If something grows continuously or at all times, all right, we call that continuous growth. All times. We're talking every day. All right, every hour. All right, every minute. All right, every second there is change. Okay, for example, we are growing every second of the day. I mean, there is no time that we're not growing until we flatten out. I mean, obviously, there is a maximum or a time where we stopped, let's say, growing vertically, although not horizontally most times. All right, but things do grow uh, continuously at some point. Most things in real life, though, do have a point at which they stop growing. Otherwise, there'd be problems occurring in all sorts of places. So, but through a stage of their life, there is what's called continuous growth, and we'll take a look at that portion of the life where there is continuous growth. In terms of money, though, uh, that could be never ending. Okay, the classic example when I'm talking about, all right, we're talking about the growth of money. Let's say if you leave in a bank where it compounds continuously. All right, so the classic example, all right, is when money, all right, is left in a bank account. Oops, got to spell that right. Bank again. There we go. In a bank account, which is compounding continuously. And if you don't know what that means, well, we're going to talk about it. We're going to talk about compounding, and we'll talk about the way it compounds. But usually, it compounds continuously. That is a classic example. It's called continuous growth. If you leave it in either a bank account, whether it's a stock or a bond or mutual fund or a simple savings account, things compound what are called continuously at different rates. Okay, whether it's compounding quarterly, monthly, quarterly, uh, daily, okay, every second. I mean, there's different ways to compound your money. We'll get into a discussion about that. Now, sometimes growth is totally different. We call that discrete growth. And sometimes there is a sudden change in population. Okay, when that happens, when there's a sudden change in population, we call that discrete growth. All right, such as after, let's say, a well, after a certain amount of time. Excuse me, let me back up here. A sudden change of population after a certain amount, all right, of time. We call that discrete growth. We can think of this as, let's say, as the stop and go type of situation. Okay, stop and go type of a situation. For a while, nothing happens, and then there's a sudden change in the population. We call that a transition, all right, which we're going to be talking about quite extensively here. And a transition, all that is a regular, okay, time interval. A regular, I'm going to say, well, I'll say time interval, okay, of time between changes of population. For example, usually it takes 9 months for a woman to conceive and have a baby. So the change in population is every 9 months. So the transition is a 9 month transitional period. And then there's a sudden change in population. There's an added kid in the family, okay? That is what a decent example, or as typical example, what's called discrete growth. For a while, nothing happens. Like for 9 months, nothing can happen, right? And then all of a sudden, a woman gives birth to a beautiful baby, and then there's one more member in the family, right? Boom, a sudden change in population after a certain amount of time, like 9 months. Okay, that is an example of discrete growth. All right, so examples of this type of growth, well, animals with animals, and that's including us, by the way. All right, animals or people, animals with consistent, all right, breeding patterns, okay? Okay, and that includes us too, by the way. And when I say patterns, I'm talking about seasons. For us, we have consistent 9 month breeding patterns, okay? And I know it varies a few days or even a few weeks actually for some people, but it's fairly consistent, okay? And that goes for all animals on the planet. They have a consistent breeding pattern, okay? The next type that we could take a look at is an inanimate case, which is bank accounts, all right, which earn interest at different intervals. And we'll talk about that specifically because it's a big topic for you guys, especially since you guys are about to jump into the real world. Some of you, even if you go to college, all right, pretty soon you're going to be on your own, and the concept of money is going to be a huge important factor in your life. So we better talk about it some. So bank accounts which earn interest at regular intervals. Okay, what am I talking about? I'm talking about compounding monthly, quarterly, and let's say annually. Okay, and if you're not sure about what I'm talking about here, and if you never really dealt with money that much, don't worry about it because we're going to have a big discussion on it. Okay, we're going to take a look at how money grows at regular intervals, whether we invest it monthly, quarterly, annually, or so on. All right. Now there are two basic questions which we can talk about. What will happen with a given population over time? Meaning that will it increase? Okay, or will it decrease? Okay, what will happen to that? And then the next question is, if it does increase, then by how much? If it does decrease, then by how much? All right, those are important questions, especially when it comes to money. And then, of course, what are the long-term patterns of growth? When I say patterns, is I'm asking, can we write a rule to define it? Okay, a rule, let's put that in parentheses there, like a recursive or an explicit function to define it so that we can calculate future values. Whether it goes up or down, it really doesn't matter. One of the big things to determine is uh, or to do in, let's say, in the stock market or in economics is to predict the future, right? Well, people do that by mathematically modeling the situation and writing functions which can predict the future, whether it's increasing or decreasing. All right, so the question is, can we write a rule to define it, a recursive rule or an explicit rule like, well, you'll see it here in a little bit. Okay, to answer these questions, we got to find the rules which govern the transitions. Okay, we call these the transition rules. Transition rules, okay. For any transition rule, you need to know the following. Let's highlight this transition rule. All right, first of all, you need to know two things. When does the change happen? When does the change happen? You need to know that. Like, does it happen every 9 months, like in people? People usually take 9 months to give birth to a newborn. All right. Uh, or it could be money. Do we compound the money every week, every day, every month, every quarter, which means every 3 months? Do we do it once a year? I don't know. What is the transition? When does the change occur? Okay. And then secondly, how is the population changing? Okay. How is the population? And when I say population, it could refer to money too as well. This is a general term. All right. How is it changing over time? Okay. How much? By how much? Per time level. Okay. By how much? Over time. Okay. How is it changing? Is it doubling? Is it tripling? Is it increasing only by one or by two? Or is it decreasing by 50%? I mean, what's going on in the situation, right? So over, when and the how. We got to know those two things. All right. The second thing is, or the next thing is, you have to know uh, what the uh, I'm sorry, is how to describe the population sequence. Okay, and so what we're going to do is we're going to use P for population, and we're going to be using subscripts. So the question is what do the subscripts mean? Okay, so this P sub 0, let's start from the beginning here, represents our initial population. So this is important, okay, because you have to understand our subscripts in mathematics, otherwise you won't even understand what's going on. All right, so what's going on with the population over time? So we call P sub 0 the initial population. Initial population, okay? It could also represent the starting point or the seed. Different ways to think about it, okay? The starting point, all right? Or what's called the seed, okay? You're familiar with that. The starting point also. So this is the seed. All right, after one transition here, you have the first generation or the population of the first generation. So this represents right here, this period of time represents the first transition. All right, it could be 2 months, it could be 1 year, it could be 6 weeks. We really don't know. We don't know that time interval. All right, but it's a period of time that goes by, and after one transition, we get what's called the first population. So P sub 1 is the, excuse me, the first generation, is the first generation or the population after one time period. When I say transition, I'm talking about a time period. Transition, oops, gotta spell this right, sorry. Transition time period, okay? So let's not misunderstand me here, okay? So after, let's say, 2 months, that's the first generation, okay? After another transition, all right, this is the second transition right here. All right, you get P2, P sub 2, which represents your second generation, or the population of the second generation, okay? For P for population too as well. All right, so after two transitions or time periods, you get the second generation. After three, there's another transition here. This is the third transition here. So after three transitions, you get the third, okay, generation, or the population of the third generation. So this represents three transitions here. All right, and in general, okay, all the way to P sub n here, this represents your nth, all right, generation, or the population of the nth generation after n transitions here, or n time periods. Again, you can think of it as time periods as well. Time periods, transitions, they're the same thing, just new terminology here, guys, okay? So P sub 4 is after 4 transitions, P sub 5 after the population after 5 transitions, and so on, all the way after n transitions. Well, you get P sub n, which is the nth generation or the population after n time periods, okay? So we're going to be using this notation here when we talk about what's called a population sequence. Population sequence. Okay, P sub n. All right. Now let's get into some basics examples here and get a little bit more concrete. Okay, now a population sequence, all that is a list of numbers that represent the changes in the population. Okay, the list of numbers, all right, that represent, all right, the changes in population. All right, over multiple transitions. And now again, when I say transitions, I'm talking about time periods. All right, a list of numbers that represent the changes in population over multiple transitions or time periods. This is the population sequence. P sub 0, then P sub 1, P sub 2, P sub 3, P sub n. And remember, P sub 0, well, that's just the seed. Okay, so let's get specifics. The seed, or the starting population. And when I say population, this is a general term, okay? The population may be, it may be inanimate, it may be money, it may be referring to people, it may be referring to animals, inanimate objects, it could be even money. Okay, so population is a general term. P sub 1 stands for the size of the population. Size of the population after one transition. After one transition, or you can say time period. Now I know I'm being redundant, but I'm hopefully helping you guys out by being redundant, because I'm trying to get in your head that a transition and time period are the same thing. And the subscript right here, the 1 stands for the transition, okay? So it's the population after one transition. P for population, and 1, the subscript, standing for the number of time periods that gone by. And then after P sub 2, P sub 3, all the way to P sub n, it's the size of the population, okay, after n transitions. I'm just reiterating and specifically defining what I said earlier, okay, after n transitions, or you can say time periods. Okay, now understanding that, let's get into an example here, a real example. Simple, but real. All right, so you can make sense of this. All right, so we got number of cards produced is expected to increase. Let's underline the key terminology. It's going to expect to increase by 25 every month. So that's a plus 25 every 2 months. This is your transition right here. All right, here's your transition or your time period. Transition or what's called a time period. Okay, so we're dealing with cars. They're increasing by 25 cars every 2 months. If the company started with 100 cars, ooh, there's your seed. All right, which is the starting amount. AMT is amount, okay? Find the population sequence, okay? Now that means what's P sub 1, P sub 2, P sub 3. And that's what we're going to do. It's a very, very simple example, although it kind of illustrates the idea in a very simple fashion. So just go with it here. So the transition is what I said just a minute ago. It's every 2 months. And so let's define it here. So every 2 months, okay? Transition rule, okay, we're going to write it recursively at first. Recursively, the transition rule, all right, P sub n is going to be equal to the previous month, all right, P sub n minus 1, all right, the previous population, and if it's increasing, it's going up, so we're going to use addition here by 25, all right? All right, it's increasing, look at this, increasing by 25, so obviously we're adding 25 to the previous one, and you guys already know this, represents the previous population, previous. All right, so you just keep on adding 25. So what's really going on here? So let's get right into it. We got population here, which represents the number of cars. All right, here, P sub n. The initial population, P sub 0, this is your seed. Right here is right here. Here's your seed. That's 100 cars. Okay, so we got 100 right here. All right, and after one time period or 2 months, ooh, after one time period, this is 2 months, you have one transition, okay? Again, this is transitions up here. This n equals 1 is the transitions, right? So P sub 1 stands for the number of cars after one time period. So after 2 months, well, it increased by 25. So you got to add 25 to it. Well, 100 plus 25 is 125. Whoo! Oh my gosh, we got 125 cars after 2 months. All right, and then what you have to do is, well, to get to the next transition, another 2 months go by, right? This is stuff. And we have to add 25 to 125. And well, we get 150 cars, right? This is cars, cars, cars here. Okay, after 2 time periods or 2 transitions, or which equals 4 months, by the way, all right, you have 150 cars, okay? Well, 2 more months go by, which is a transition or a time period. And what's the population of the third generation? Ooh, well, you have to add 25, right? And this is tough stuff. 150 plus 25, well, it's 175 cars. That's how many cars after, let me see, 2 and 2 and 2, that's 6 months. So this is after 6 months. After 6 months. Okay, now let's answer some basic questions. Basic questions about what's going on here. Okay, so how many months have passed for P sub 9? Well, P sub 9 stands for the size of the population after 9 transitions. That's the first thing we have to understand. The size of the population, all right, after 9 transitions, or time periods, all right? Well, how long is it a transition? Tell the person next to you, I mean, how long is a transition? Look up here. How long is a transition? Well, it's You got it, 2 months, right? And if you go through 9 transitions, all right, so 9 transitions, and there's 2 months for every transitions here. Well, it kind of sounds like 18 months. All right, you have to multiply the number of months per transition, right? So you have 9 times 2 or 18 months total. That's the size of the population. And if we wanted to figure it out, we just keep on adding 25. We do that multiple times to get P sub 9. All right, number 2, or 1b, excuse me. What is the number of cars? Ooh, after 5 transitions? Well, that's P sub 5. Well, we know P sub 3, so let's find P sub 4 first. All right, so P sub 4 is 175 plus 25, which is 200. All right, P sub 5 is 200 plus 25 equals 225 cars. All right, no big deal. All right, next question. What is the number of cars produced after 1 year? Well, 1 year. Well, we know. Let me see, we're seniors. Okay, 1 year equals 12 months. 12 months. So the question is, how many transitions is that? All right, 12 months. Let me see. How many periods of 2 months? How many 2 month periods do you have in 12 months? Well, that equals, let me see, 12 divided by 2 or 6 transitions, right? Transitions, right? Every 2 months is a transition. So you got to divide this number by 2. Okay, divided by 2, tough stuff. So what we need to find is P sub 6. The number of cars is P sub 6. And if we know P sub 5, well, we just add 25 to it. So 225 plus 25 equals 250 cars. Okay, hopefully it makes sense so far. Just dealing with some basic examples here. All right, let's take a look at one more model here. Check this out. Michael expects to double his profit. Ooh, double his profit. All right, times by 2 every 6 months. Okay, there we go. There's a transition here. That's the transition. Transition. And so, okay, that's transition right here. Every 6 months. Every 6 months. I'm just interpreting as I'm reading here. So he wants to double his profit every 6 months of his investments that he's already earned. He has already, okay, earned $120 profit. Well, guess what? If he already earned it, that becomes the seed. All right, so the seed here in the beginning, he's already earned 120 bucks. There's your seed. Now, in this case, we're dealing with money. All right, so our population deals with money. And that's what I was saying earlier, that you have to understand that population is a general term. It could be people, animals, money. It can mean a lot of different things. So you got to go with the flow on these things and understand the context of the problem. The transition rule, P sub n, is going to be equal to double, okay, the previous. Double is profit every 6 months. So 2 times the previous P sub n minus 1. Double the previous month. Double previous, that's keyword, amount, AMT. All right, multiply by 2. Simple. All right, so knowing that, all right, and this is profit now, okay? Because we're talking about profit here. All right, after 6 months, after one transition, n equals one transition or time period, which is 6 months. All right, so this is 6 months goes, right? Plus 6 months. What's the amount of money that you have? Well, you double, right? So you got to multiply it times 2. Times 2. 2 times 120 is 240. All right, and then 6 months goes by, or after 12 months. So you times by 2. All right, and you get 480 bucks. And after another 6 months, which is a total of 18 months, all right, you have to double that. And that's 960 bucks. All right, 960 bucks. And then you got to double again, and that becomes 1920 bucks. That's 1800 plus 120, 1920 bucks. All right, we're doing well. After 2 years, basically, or 4 transitions or time periods, We went from 120 to 900, 1920 bucks. All right, profit, which is not too bad. All right, after 2 years, I mean, you start off with 120 and then you end up with 1920. That's pretty darn good, guys. All right, how much profit, all right, is Michael making in the eighth generation? Well, to figure that out is like how many months have gone by. All right, so let me see. So in the eighth generation, well, we got that's let me see, 8 times 6. That's 48 months. So eighth generation, 8 times 6, 8 times 6. Whoop, let me write that better. See, every transition is 6 months, right? So 8 times 6 equals 48 months. All right, that's 4 years. All right, that's 4 years. So after 4 years, how much profit? Well, let's figure this out. So piece of 5, you got to take 2 times 1920. All right, you could do this on the calculator, of course. You get 3840, 3,400, excuse me, 3,840 bucks. Piece of 6 is 2 times that, the previous. All right, what do you have? You have 7,680. You can verify this. Do this obviously on the calculator if you can't do it in your head. And piece of 7 equals 2 times that, the previous. All right, which is equal to 15,360 bucks. All right, and so what you want to do is you double that, and so piece of 8 would be 2 times 15,360, which would be 30,720 bucks. All right, verify that on the calculator. You enter in 1920, you go times 2, times 2, times 2, times 2, times 2, and then you end up with 30,720 bucks after 48 months or 8 transitions. That's how it works, my friends. Okay, that's what doubling does. Doubling is pretty powerful. You can get some big numbers real quick. All right, now that's after, this is 4 years. All right, because there's 12 months per year. So 48 divided by 12 is 4 years. All right, but in this case, the question is how much profit will we make in the third year of investing? Okay, well, let's see. After 3 years, let's see, there's 2 transitions per year. Or you can do months, okay? However you want to do this. So it's 3 times 12, let's see, 3 times 12 is 12 months per year, is 36 months. All right, and then we have to divide it by 6 because there are 6 months per transition. So 36 divided by 6 gives you 6 transitions or time periods. Okay, every 6 months there is a time period. So there's 2 time periods per year, and if there's 3 years, there's 6 time periods. So 6 transitions or time periods. Time periods. You can think of it, there's different ways to calculate it. I showed you one way. The other way is to understand that if it's every 6 months, guys, there's 2 time periods per year, and if it's 3 years, 2 times 3 is 6. So 6 transitions or time periods. So what we would need to find here is how much profit is a piece of 6. Half of these questions here, guys, is figuring out what you want. All right. And if you understand what you're looking for after the number of transitions here, then it's easy. We just already found it right up here. Here's piece of 6. Happens to be right here. So we don't have to figure it out again. We already know it. So 7,680 bucks. Profit. All right, after 3 years. Okay, and this one here says how many years into the future this piece of 36 represent? Okay, so let's understand this. So uh, one transition here, one transition equals 6 months. 2 transitions equals 12 months. I'm trying to do a common sense approach here. So 12 months or 1 year. Okay, if that's the case, then piece of 36, will be, that's after 36 transitions, right? And if there's, let me think this way. So piece of 36, So P sub 36, this is 36 transitions. Now we know that every 2 transitions is 1 year, right? So 36 divided by 2, that's 18 years, okay? Because we know that there's every 2 transitions equals 1 year. And if we're talking about 36 transitions, well, we got to divide it by 2 to get to the number of years. All right, so 36 divided by 2 is 18. So P sub 36 represents the amount of profit after 18 years. This is the amount of profit, okay, after 18 years. That's what that is. If we wanted to figure it out right now, we'd just list them out, which would be a real big bummer. That's why we need to know more. And there are ways to figure that amount without listing them all. That comes in time, and that gets us into the next section. All right, section 10.2. Right now, we're just understanding the basics of how we write it and how we think about it, and what does all this notation mean, okay? So this is Mr. Ainsworth. We are done with a little intro lesson right here. Stay tuned for our next lesson in section 2, where we talk about what's called linear growth model, okay? And we'll get really into it. All right. You guys have a good one. Make yourself proud. Do your best in school. I'll see you in my next lesson. Bye-bye.